Okay, now we're going to look at question 11 on page 345. Okay, here it is. So question 11 is a rung on a hamster wheel. A hamster wheel is like a Ferris wheel for hamsters. A rung is like a rung on a ladder, so the stairs on a ladder. So it's the things they stand on to make the hamster wheel go around. So the hamsters actually run the Ferris wheel. They spin the thing themselves by running on it like a treadmill, and it just keeps going around and around. So a hamster on a rung on a hamster wheel with a radius of 25 centimeters. So the wheel is going to have a radius of 25 centimeters, so a diameter of 50 centimeters. Is traveling at a constant speed. It makes one complete revolution, so one full circle, in 3 seconds. The axle of the hamster wheel is 27 centimeters above the ground. Now the axle is the center of the wheel. Okay, so that's where the axle is. So it's 27 centimeters above the ground, and the radius is 25 centimeters. That's so that it doesn't actually hit the ground. It's only 2 centimeters above the ground at the bottom. Okay, so you want to sketch a graph of this. For the rung above, the height of the rung above the ground in terms of time, so one complete revolution, beginning when the rung is closest to the ground. Okay, so when the rung is at the bottom. Okay, so describe transformations of the coast graph to get this, and write the equation that models this situation. Okay, so I'm going to write down some of this information here. So we've got a radius of 25 centimeters. Okay, and then we've got one cycle or revolution takes 3 seconds. Okay, now let's take a look here at, so I'm going to have the ground right here. There's a picture of the Ferris wheel, and the Ferris wheel is like that. Okay, center of the Ferris wheel right there. That distance from there to the ground is 27 centimeters, and the distance from the bottom to the center is 25 centimeters, okay, because that's the radius. So that would make this distance here 2 centimeters. Okay, so now we're going to draw this graph, okay, and try to leave lots of space here. So because the axis is here at 27 centimeters, or the axle, that's going to be where the axis is for this. So I'm going to have a low horizontal axis. Okay. It looks something like that. Now this is going to be the d-axis again, and this is the time axis. And we know that the axis of the function is going to be at 27 centimeters. So we'll put it right about here. Okay, this is our axis. So y equals 27, or actually d equals 27, sorry, d equals 27. Okay, and then the bottom will be about 2 centimeters, so this is not to scale. And then the top, 25 above that, would be at 52. Okay, so that's going to be 52, 2, so that would give me a diameter of 50. Now, because he starts at the bottom of the hamster wheel, this is going to be our starting point. And now we're going to mark off quarter periods. Okay. Okay, so quarter period so that we can draw one cycle. They want 2. So we'll do quarter periods here. So 1, 2, 3, 4. I'll draw in 1. So from here to here, then this to the top, back down, and then back down to the bottom here. Okay, so okay, so that's one cycle, and one cycle takes 3 seconds. So now I'm going to do it again for the second cycle. There, there, and about there. Okay. And this would be what it looks like, that rung on the hamster wheel. So here's a rung right there. It's going to go around and around and around. Okay, so it goes up, and then it goes back down again and again. Okay, so that's going to be in a total of 6 seconds for 2 cycles. So that's going to be 1.5, and that's going to be at 0.75, which would make this 2.25. Okay, and so on. So that would be our graph. Now, how is this transformed from a coast graph? Well, a coast graph normally starts at the top. So this is going to have a negative a value to start at the bottom. It's been vertically flipped. Okay, it's going to have an amplitude of 25. So it's going to start off with negative 25. And then you have to figure out the period from this, the k value from this period of 3. It's not been horizontally translated from a negative coast graph, but if you think of a coast graph, well, it has been horizontally translated to there. If you want to use positive coast, so it'll be translated forward 1.5 if you want to do that, but that's not the simplest version, so we'll do the simplest version. So d of t equals a cos k t minus c plus d. Let's fill in what we know. So here's the basic form of that function. So we know d is 27. We know a is going to be negative 25. And c is going to be 0. Unless we used positive 25, then c would be 1.5. So minus 1.5 to move it forward. Okay. Now k. So k, as we recall, equals 2 pi over the period, which is 2 pi over 3, and that would be the best way to leave it. Okay, so d of t equals negative 25 cos 2 pi over 3 t plus 27. Okay, that would be the function for this graph. Now, if you had to do it in terms of sine, well, this looks like a sine function that's been moved forward 0.75 units. Okay, so you could do or d of t equals, and I'm going to say it's a positive 25 because this is going up. Okay, so 25 sine 2 pi over 3, period's still the same, so the k value is still the same, and t. So because it's been a sine function moved forward, I'm going to put minus 0.75 and then plus 27. So this is another option for that function in terms of sine. Okay, that's it for that one.